Hello, welcome back to the class. In the previous session, we discussed about the theory behind shear. Okay. In this class, we will solve a problem. The problem goes like this. Determine the shear capacity of the beam of section in each of the following cases. In each of the following cases. So, case A, size 230 millimeter by 500 millimeter, effective depth reinforced with 3 numbers of 16 millimeter diameter with Fe 415 grade steel and 6 mm diameter MS stirrups at 130 millimeter center to center. Concrete is of M20 grade. Concrete is of M20 grade. So, there is another case, case B, size 230 millimeter multiplied by 720 millimeter, effective depth reinforced with 5 numbers of 16 millimeter diameter, with F415 grade steel out of 5 numbers of steel bars, 3 are straight bars and 2 bars bent up at 45 degree with 8 millimeter dia stirrups at 300 millimeter center to center with Fe 415 grade steel consider M20 grade concrete. So there is one more case, that is case C. So I am going to write that part when I take the class in the next session. So in this session I will try to cover these two cases. So the problem goes like this. Determine the shear capacity of the beam section in each of the following cases. As I said, we have 3 cases. I have written only 2 cases as of now. So first case is size of the beam is 230 millimeter with 500 millimeter effective depth, not the overall but the effective, reinforced with 3 numbers of 16 mm diameter with Fe 415 grade steel and 6 millimeter diameter, 5 stands for diameter, MS, that is mild steel stirrups at 130 millimeter center to center. Concrete is of grade M20. That is the first case, that is case A. Second case is this. Now I am going to concentrate on case A first. Okay. Please open page number 73 of the code book because you need to refer page number 73 of the code book. Please write down this figure. We have 3 bars of 16 millimeter diameter. And 230 millimeter by 500 millimeter effective. Okay. So, this is a beam. Okay, it runs throughout this span, and I have written only half of the beam, and this beam is supported by this. It may be a wall or some other support. Okay, and as per the design, what we have done is we have provided 3 tension reinforcements. So, 3 reinforcements, each bar of diameter 16 millimeter, and we have provided stirrups as per the design, and the stirrups are of 6 millimeter diameter, and they are provided at a spacing of 130 millimeter center to center. So, that is, this is 130 millimeter, and we are going to represent the spacing as S suffix V, that is equal to 130 millimeter center to center. Okay. And we have 2 legged stirrups. So, if you take one stirrup ring, it has 2 legs. Is it clear to you? Then when it comes to the dimensions of this section, width is 230 millimeter, and the effective depth is measured from the extreme compression edge to the centroid of the tension reinforcement, that is 500 millimeter given. So, total depth in this case we do not need it, we only need effective depth, that is what given in the problem. So, we are going to go and proceed with the problem. So, what we need to do is determine the shear capacity of the beam. So, shear capacity in the sense, what is the maximum shear, okay, at which the beam is likely to fail, that is the design strength or the ultimate strength or the factored strength of the section in shear we need to find out. So, when it comes to shear, as I discussed in the previous class, shear is going to be carried by concrete as well as the stirrups, that is total shear will be carried. So, total shear due to the external load coming on that beam will be taken care, that means will be carried by the reinforcement and by the concrete. When it comes to the concrete, so the shear capacity of the concrete depends on the percentage of reinforcement. Okay. And once we start solving the problem, I am going to explain you in detail what it is. Now, what I do is, first I am going to write the shear capacity or the shear strength equal to, that is the total shear capacity, the shear capacity equal to shear capacity of concrete plus shear capacity of steel. Here it is tension steel. So, I am going to write the shear capacity or the design shear strength or the ultimate design shear capacity as VUD equal to shear capacity of concrete. I am going to write that as VUC plus shear capacity of steel is given by, I am going to write VUS, that is of course suffix US. So, I am going to call this as equation 1. So, I am going to find out this one, this value, shear capacity of concrete separately and the shear capacity of steel separately. Here steel is nothing but the stirrups. Okay? Remember, when I say steel, I am talking about the stirrups. So, I am going to find out this. So, once I once these two values are found out, so I am going to add those two values to get the total shear capacity. Okay. Now let me start with VUC. That is, what is the shear capacity of concrete? So if you look table 19 on page 73 of the code book, please open it. So on page 73, if you look at the left column, 100 AS divided by BD, that is the percentage of reinforcement. Okay. Go horizontally along that line, you see M15, M20, M25, etc. up to M40. So for, say for example, if you are using 0.75% of the tension steel, here AS refers to the tension steel, because shear capacity of concrete depends on the percentage of this tension steel. Is it clear to you? So, for example, if I take 100 AS by BD equal to 0.75, and if I am using M20 concrete, then the shear strength of concrete is 0.56 Newton per millimeter square. Is it clear to you? So 0.56 Newton per millimeter square multiplied by the effective area. Effective area is the width multiplied by the effective depth, will give you the value WUC. So what in case the percentage of reinforcement is, say, 0.8, because if you look at the table, left column, we are going to see the values corresponding to 0.75% of steel, 1.25, that is at 0.25 increment. So what in case if you get the percentage of steel, this steel, some fractional values other than what we have in the table, say for example 0.8. So we don't have a value for 0.8. So that's why what I do is, so I am going to take the value corresponding to 0.75% of steel, that is 0.56 Newton per millimeter square, and corresponding to 1% of steel, I am going to get the strength of concrete equal to 0.62 Newton per millimeter square, and I am going to do some interpolation, linear interpolation, to get the value of tau C. Tau C is the design shear strength of concrete for 0.8% steel. Is it clear to you? So let us proceed with the problem here. So before proceeding, first what I need to find out is the percentage of tension steel. For that, what I do is, I am going to find out what is the area of these 3 bars. Therefore, area of tension bars, I am going to write AST. See, in the code book, in the table 19, in the leftmost column, it is given as 100 AS divided by BD. When it says AS, here I am calling the same thing as AST, that is my choice. So pi by 4 into 16 square. This is the area of cross section of the bar, and we have 3 such bars. That is equal to 3 multiplied by this. I am going to get this value as 603.20 millimeter square is the area of cross section of the tension steel. So now I am going to find out what is the percentage of this steel. Therefore, percentage of tension steel equal to AST divided by BD divided by, multiplied by 100. That's what given in table 19 on the leftmost column. It is given as 100 AS divided by BD. Instead, I have called that as AST divided by BD multiplied by 100. That is equal to, what is AST? 603.20 and B is 230 and D is 500 multiplied by 100. That is equal to, so what is the percentage of steel? As per the calculation, the percentage of reinforcement is 0.525%. Okay. So go to table 19, page 73 of the code book, and the type of concrete we are using is M20 grade. So for M20 grade, for 0.525, do we have a value? Have a value? No, we don't. So we have a value for 0.5 and we have a value for 0.75% of the steel, which is equal to 0.56, and 0.525 comes in between those two. So I am going to do some linear interpolation to find out the shear capacity or shear strength of concrete corresponding to the steel area of 0.525%. So I am going to write AST BD from table 19, page 73. I am not going to write IS 456 2000. The reason is, by default when I say this, I am referring to the code. So 100 AST by 100 multiplied by AST divided by BD and tau C in Newton per millimeter square. That is the shear strength of concrete. So again, if you go back to the table 19, if you look at the top, it says table 19 design shear strength of concrete. What is the symbol? They have used tau C as a symbol, and that is the one I am using here. So for 0.5% steel, the shear strength of concrete is 0.48 Newton per millimeter square. And for 0.75, the shear strength of concrete is 0.56 Newton per millimeter square. So what is our value? Our value is 0.525. 0.525. So what is the value of tau C? So for that, as I said, I am going to do linear interpolation. Therefore, shear strength of concrete tau C equal to, so corresponding to 0.5%, it is 0.48 Newton per millimeter square. So it is 0.75 minus 0.50. It is 0.56 minus 0.48, and it is 0.525 minus 0.50. So the value I am going to get is 0.488 Newton per millimeter square. That is the shear strength of concrete for 0.525% of tension steel. Is it clear? Once we have this value tau C, this value is for unit area. So multiply that value by the effective area of the concrete. section. Therefore, shear strength of concrete, shear strength of concrete is VUC, that is given by tau C multiplied by BD. What is tau C value? 0.488 Newton per millimeter square. 0.488 multiplied by B is 230, D is 500. So, I am going to get the value in terms of Newton and I am going to convert the same thing to kilonewton by dividing this by 1000. Okay. So, I am going to get the value of VUC equal to 56.12 kilonewton. So, I am going to call this as equation A. Okay. So, in this equation, I calculated VUC value, V suffix UC value, that is the design shear strength of concrete, that is equal to 56.12 kilonewton, and I have called that as equation A. The next step is I am going to find out VUS, that is the design shear strength of steel. When I say design shear strength of steel, I am talking about the stirrups, not this tension steel. So, let us go with the next one. VUS equal to what? So, if you look here, what kind of stirrups we are providing? We are providing 6 millimeter diameter stirrups at 130 millimeter center to center. What kind of stirrups we have? We have got mild steel stirrups. That is, for mild steel, stirrups, Fy equal to 250 Newton per millimeter square. That is the characteristic yield strength of the mild steel. And what is the diameter of this stirrup? That is 6 millimeter. Therefore, area of two-legged stirrups equal to, so I am going to write ASV as in the code book, pi by 4 multiplied by 6 square will give you the area of cross section of each leg. If I multiply that value by 2, because I am going to get the area of cross section equal to 2 times. So, the area is 56.55 millimeter square. See, whenever shear acts like this, due to complementary shear, the shear will also act in this direction. Okay, when the shear acts in this direction, there will be two stirrups, that is two legs of the stirrup resisting the shear caused due to the external load. That is the reason why we are considering twice the area. Okay. So, once we have the ASV value, so we need to find out what is the shear capacity of the reinforcement. So, again here the shear capacity of the reinforcement means shear capacity of the stirrups. Again, if you go to page number 73, under 40.4a for vertical stirrups, we have VUS equal to 0.87 Fy ASV D divided by SV. So, from 40.4a, page 73, we have VUS equal to 0.87 Fy ASV divided by SV. So, that is a formula we have, and Fy ASV D is the formula we have. So, substitute the values. What is Fy? Fy is 250 Newton per millimeter square. ASV is the area of cross section of two legs, and each of leg of the bar of 6 millimeter diameter, and D is the effective depth which is given, that is equal to 500 millimeter, and SV is the spacing of the stirrups. This is SV. Stirrups are provided at 130 millimeter center to center. So, let us substitute all the values first. So, that is equal to 0.87 multiplied by 250 multiplied by ASV is 56.55, depth is 500 divided by spacing is 130. So, we are going to get the value in terms of Newton. So, I am going to convert the value into kilonewton by dividing it by 1000. So, I am going to get VUS equal to 47.30 kilonewton. kilonewton. So, we calculated what is VUC, and we calculated what is VUS, and I am going to call this as equation B, and by substituting the value of equations A and B, that is the values of VUC and VUS in equation 1, we are going to get the value of VUD. Okay. VUD equal to 56.12 and 47.30. 47.30, that is VUD equal to, that is 104.42 kilonewton. Okay. This is the design shear strength of this section with 3 tension bars, each of diameter 16 millimeter, and with 2-legged stirrups of diameter 6 millimeter and of grade mild steel. So, this is the value. Okay. And one more check we need to do. Again, if you come back to the code, so if you refer page number 72 under 40.2.3, it says 40.2.3 with shear reinforcement, under no circumstances, even with shear reinforcement, shall the nominal shear stress in beams tau V exceed tau C max given in table 20. So once we start designing, you will know what tau v is. Tau v is nothing but find out what is the maximum shear developed due to the external load. Say for example, if I take a simply supported beam under UDL, so the support reaction is going to be WL by 2, that is going to be the maximum shear force. So using that shear force, divide that shear force by the area, effective area of cross section of the beam, and you are going to get the actual shear stress, that is actual in the sense design shear stress developed, and we are going to call that as tau v. Once we do that, that should be compared with table 20 on page 73 for the given grade of concrete. So in case, say for example, for M20 concrete, tau c max is 2.8 Newton per millimeter square. In case tau v value exceeds tau c max value, no matter what, no matter how much reinforcement you have provided, no matter what grade of concrete you have provided, you have to increase the section, because design shear stress is exceeding tau c max value. That means the dimensions of the beam, that is the breadth and the effective depth you have provided, is not adequate to take care of the shear. Is it clear to you? So in this case what I do is I am going to put one more check. So I am going to find out what is the maximum shear capacity of this section by taking tau c max value. Okay, and this value should be less than tau c max multiplied by BD. In case this value exceeds that value, tau c max multiplied by BD, then we are going to take tau c max multiplied by BD as the shear capacity of the section, not beyond that. So let us do that. Now, as per 40.2.3, page 72, page 72 and table 20 of page 73, VUD max equal to tau c multiplied by BD. Sorry, tau c max multiplied by BD. So for M20 concrete, if you look at the table 20, it is 2.8 Newton per millimeter square. That is 2.8 multiplied by 230 multiplied by 500. I am going to convert the value into kilonewton by dividing it by 1000. Okay. So I am going to get the VUD max value equal to VUD max value equal to 463.68 kilonewton. So that is VUD is less than VUD max. Therefore, design shear strength or shear capacity of the section equal to 104.42 kilonewton. So this should be your final answer. I repeat, in case VUD value exceeds VUD max, that means instead of 104.42, if this value becomes say 470, kilonewton. Then 470 is greater than 463.68. In such cases, you take 463.68 kilonewton as the VUD value. Is it clear? Let us go with the next case in the next session. So, that is it. Thank you.